first session on the element copper, we focused on direct observations. That's where science starts, the ability to observe. And when we observe and we get information, we have to learn how to classify it. And for instance, we observed with the element copper, we observed, let's say, color. Now, if we classify color, we have to use a scheme. It's binary, X and non-X, for the information on the variable. For instance, we could say the color silvery. And then everything else in the set is non-silvery. This would be one quick way of identifying copper, because almost all the elements are silvery. And what's left would be basically gold and copper, so it would be in the non-silvery set. If we classify density, is what we talked about in the last session, it gets a little more complicated. You could classify just by high, medium, and low density, like gases and liquids and solids. But we could classify by numbers, and what we want to do is use all the information we can get. And we're going to look at some of the efforts to develop what's called patterns in density. And now we introduce that word, pattern. That is going to be extremely important in chemistry. When we examine patterns, we get information beyond the element itself. We get the information on how the element relates to a larger context. One event can tell you very little, but a whole pattern related to that event can give you a lot more information. For instance, patterns are in every subject. In art, for instance, we have, my goodness, going back to, and I'm going to be off on my dates here, in the range of about 1480, 90, Leonardo da Vinci. And one of the famous patterns I remember is the Vitruvian Man. Get that right, Vitruvian Man. And the Vitruvian Man was Da Vinci's search for the patterns, how man literally may relate to the whole cosmos, the Vitruvian Man. One of the 20th century artists that I particularly found interesting was Escher. And Escher's tessellations are great, and I have one I'm showing right here. But so there's in art and music and mathematics and just about any area. In fact, I would say with all patterns, they're almost an essential to keep us from going crazy, because we are experiencing a steady stream of sensory experiences. That makes sense? Thousands of little events are happening, one after another, microsecond by microsecond, if you would. But all these sensory experiences, if our brain tried to figure each one out, we would go crazy because we couldn't put it all together. But our brain, fortunately, works with patterns. Unfortunately, sometimes our brain doesn't see patterns as well as it should in science, and we need a little help. So we're going to be looking for patterns and sometimes exceptions in patterns called anomalies. All right, okay. So the first thing we're going to do is go back to our density. The density of copper was 8.9 grams per cubic centimeter. That's an individual piece of information. We call it data. But if we put that density in the scheme of all the densities that you see here from all the elements of the periodic chart, you see that there are some patterns. You see that in general, the peaks and valleys there that the elements in what's called Group 1 of the periodic chart, lithium, sodium, potassium, rubidium, are some of the lowest densities. Okay, and in some cases you can see some variations, we could call them anomalies. They may be in a deeper pattern. So density. Now the variable that we're going to look at now is melting point. Now melting point is what we call an intensive variable, as is density. Intensive means no matter what quantity you have, it's going to melt at that same temperature. Or if we go back to density, no matter how much you have, it's going to have that same density. Intensive. Very important. The melting point of copper is not too high, 1083 degrees Celsius. 1083 degrees Celsius. What does that tell you compared to other elements? Well, there's a great range of melting points, and there's this word coming, pattern. And let's look at this massive data from the entire periodic chart, the melting points of copper. And if you just take that one section, you will see that in period 4 starts with a very low melting point. You start with sodium, that's about 63 degrees, and it climbs very abruptly. And then there's a little an anomaly between scandium SC, scandium at 1539, and it goes up to chromium 857 and it drops 1244. I call that an anomaly. Why it drops, that will be for future research. Then it goes back up to iron 1535, down a little bit to cobalt, down a little bit to nickel, and down quite a bit to, there's our guy, copper, and then a substantial drop down to zinc. Then you get over into the another section of the periodic chart. The section I just referred to, from scandium to zinc, is called the transition metals. Okay, so we could examine patterns there, and we could talk about them all we want. I should also point out that copper, when you heat copper itself, right before it melts, copper goes through a phase change. Phase. Now, what does that mean? Phase means solid, liquid, or gas. That's a phase. So when it goes from a solid to a liquid, that's melting. And it goes from a liquid to a gas, that's vaporizing. And if you see our chart, there's a little pattern there. There's a flat point when the solid is changing to a liquid. See the flat point. And then there's a very extended flat line when it goes from a liquid to a gas. So there's got to be something different happening there. But the point is, we can look at this characteristic pattern of melting if we have the information. So over and over again, we're going to be examining lots of patterns. So we're going to stop right there on this session on copper 2.